think we're set. Good morning, everybody. Welcome on in. So, welcome. We're gonna continue our discussion here. A few things to kind of take care of before we get started, and then we got to dive into chapter 2. Chapter 2 is a very dense chapter. It's possibly the most dense chapter you've ever run across in a math class up to this point. There's just a lot of stuff in there, and it's different than anything you've learned before. And I'll be honest, students find parts of it very challenging. So we'll work through that, and we'll see where things, how you feel with it, and make sure you come get help if you have questions. Thanks to those people who are throwing their name up there. If you're just on the YouTube stream, thanks for throwing your name on there. It's going to make it easier here in a few minutes when I take roll. We'll just move through it a lot faster. Couple things I want you to know about. So, oops, that's not the right page, is it? Oh, here it is. I moved it. That's what I'm looking for. So the main Ventura College webpage, if you go to it, you've got this academic calendar link up at the top. If you click that, it now includes the final exam schedule. They've released the final exam schedule for this semester. So we click it, and we go down. So here's the thing. We are scheduled in 2 weeks. So I believe the 14th is the return date to campus. We will be returning to campus at that point. Turn that sound off. We'll be returning to campus at that point, and there will be no more Zoom meetings. There will be no more recordings of the class meetings. You will be expected to be participating in an on-ground course on campus. Those of you who have taken care of your vaccine and submitted your vaccine card to the school, you should be all good to go. You're just going to show up on that first day. So I know I've had to do this a few times. I'm sure most of you have not. You'll go to campus. I'm sure it's going to be crazy the first couple of days. They're going to have these areas where you check in. So don't get there. Our class starts at 10. Don't show up to school at 9:58. You're probably going to end up being really late to class. So I would show up early that day. They're going to have like a tent, these little stations about, and you're going to go there. And before you talk to them, you fill out on your VC app. It's going to ask you, it says like daily screening, and it's going to say, do you have symptoms of COVID? And, if you don't, then you hit no. It's going to say, have you been exposed to people with COVID? And if you haven't, then you hit no. And then it says, okay, here, you're good to go. And on your screen, it gives you, if you've uploaded your vaccine card, it's going to be blue. That blue means you're all good to go. Like you're allowed to be on campus, but you're almost allowed to be on campus. You have to show that to the people at the tent, and they will give you your wristband. I, the professor, have to wear a wristband. So if I have to wear one, then obviously that means I can't let you not wear one, right? They're taking it very seriously. We are not supposed to have people around who are not wearing wristbands. If this becomes problematic, there's a whole procedure we're supposed to go through. So when you get to campus, you'll go check in. You'll get your wristband. I have to wear a wristband. I can't tell myself like, oh, you just skip getting the wristband today. It's okay. I'm a professor. No, if I have to get it, that's sort of an indication everyone really needs to be getting it. If you come to class and you don't have it, I have to tell you, sorry, go back and get your wristband. You're not allowed to be here without the wristband. If you haven't uploaded your vaccine card, then they're not going to give you a wristband. So make sure that you're taking care of that stuff now, because all it's going to do is set you behind in the class. And this is one of those classes where getting behind can mean that you're not going to pass, because it's a very difficult course to get caught up in, right? It's already challenging as a course to stay current with where things are. Once you get behind, really, really difficult to catch up. Okay, so please make sure that you're taking care of that. So, because there's really nothing I can do. If you show up on day one and you're not prepared to be in the classroom, sorry, you can't be here. You got to go. And then you're behind because there's not recordings and stuff. So make sure you're taking care of that. We also have the final exam schedule is right here. So it's just one link from the front page. One click from the front Ventura College webpage. You click academic calendar, gets you here. One more click gets you the final exam schedule. So if you can figure out when all of your final exams are. We're not allowed to mess with this as professors. I know you have professors that are like, let's do it on a different day or at a different time. Not supposed to do that. Also, we have to make something important happen on that day, whether it's a project that's due or a test or something like that. So I know you have professors that like have pizza parties on your last day. We're not really supposed to do that either. It has to do with, the state's paying us to have you in the classroom. We have to be doing something productive. I can't just decide that we're all having a party that day, but some people do that. Anyways, here's your schedule. So this works for all your classes, not just this one, not just math, all your classes. So we are a Tuesday at 10? Is that what we are? Tuesday at 10? Yeah, Tuesday at 10. Where are you? Right here, Tuesday at 10. So it looks like our final exam is May 17th from 10:15 to 12:15. You need to be there at that time. So in this class, it will be a paper and pencil test, like the old school test. You're going to show up. I'm going to give you a packet, a test with some pages in it. You're going to sit down with a calculator and a pen. You're going to write some stuff, or pencil, write some stuff out. You're going to turn it in and leave. So it's going to be a traditional type exam in that class. You can't miss it, right? The school takes finals very seriously because it's if there's ever a grade challenge down the road, one of the things that we look at is your final exam, because the final exam is going to be pretty telling about how you did in the class. And so we have to make sure, and just for professional reasons, we have to make sure that we are conducting things in a professional manner and holding people to account. So, believe me, there's been plenty of times when someone comes up to me and says, "Oh, my car didn't start this morning, or my alarm didn't go off, or I got to campus on time, but then I couldn't find a parking spot." Well, it's not about when you cross onto campus. It's about, are you in the classroom when you're supposed to be in the classroom? So, maybe you get there a little bit earlier on a day with a final or something like that. If you miss this window, you're going to get a 0 on the final, and no one wants to give you a 0 on the final. And the school's pretty strict about it, as you can see here. They even have the policy documented. Students may request a petition from the division office for a early or late exam. Those petitions have to be signed by the dean and myself before the final, and you have to have a good reason. Right, you can't. Pretty regularly, someone's, "Oh, I booked my Disney cruise, and it leaves before the final exam." We can't give you special conditions because you're going on a Disney cruise, right? The 2 times that I can think of that this has been approved, it was people giving birth during the final exam. So you kind of go, yeah, that's a medical reason. Also, it's a human reason. It's a pretty good reason why you couldn't be in the classroom at this appointed time taking the test. What are you going to do, right? So in those cases, probably if you're given birth and you can show that with documentation, we'll grant that every time. If you have some other kind of serious reason why you can't be there, talk to me and we'll figure it out. If it's just poor planning on your part, it doesn't work. We're not going to get the dean to sign it, and it's not a good reason, because what you're really asking is to get to follow a different set of rules than everyone else. And if it's just because you didn't plan well or something, then it's not really fair to everyone else who's following the proper rules. And I think most of those people who are following the rules understand, well, under certain medical conditions, we can grant an exception. But why should they have to do something at a certain time and you get to do it at a different time? You have to have a good reason for that, right? So basically, don't miss it. If you're just a no-show at the final, you get a 0. Right, so please make sure that you plan accordingly. You now know the day and the time. So if you need to request, it's a little bit different, 10:15 to 12:15, and then you're going to have to be on campus. So, some that might affect work schedules or vacation planning or something like that. You have the information. Make sure you plan accordingly, okay? If we want to get additional practice by redoing a homework assignment, will it mess up our grade? I think if you go back and look at those problems, you don't have to, you can look at old problems. You don't have to resubmit. I don't remember, we use all these different platforms. I don't think it'll mess it up, your grade. Just make sure you're always getting those green checks and you don't want the red X's. But you can go back and look. You can also do problems out of the book, right? There's additional problems that are in the actual book because you have a link to the ebook with your license. So you could go in the book and you could work problems from there and then check in the back of the book that you're getting the problems right. That would be a good way to get. That's what I would recommend for additional practice. But I don't think it'll mess you up if you're using the online homework. Okay, I did this morning, I created 3 new homework assignments. So you now have 3 homework assignments from Chapter 2. The number one thing on my to-do list today is to do the rest of the homework assignments for Chapter 2. So by the end of today, you should have homework assignments for all of Chapter 2, which will cover probably about the next 2 weeks. So you'll have some stuff to keep you working, keep you progressing. Like I say, this is for a lot of people a pretty challenging chapter. It's going to seem very different. There's a lot of notation that you have to keep track of. Certain sections are very algebra heavy. When we get into the derivative here, I think that's kind of the plan for next week. Get into the derivative. You're going to have a lot of algebra for at least one of those sections. And then we kind of clean it up and we find an easier way to do things. But for at least one section, the algebra can get intense, right? And then limits, people just, there's kind of different groups. Some people get limits right away where they're just looking at it like I'm explaining limits and they're like, yeah, that's like obvious. Why is anyone confused by this? And then there's most people, probably 3 out of 4 students, that are just completely baffled by limits at first. They're like, what are you talking about? I'm totally confused. And then probably about 25% of the class that's like, yeah, why is everyone so confused about this? So it doesn't matter which group you're in. If you're in the group that's it's a little slower to learn what a limit is, that's fine. Just keep working on it, keep practicing, you'll get it. But it does take some effort, right, on the part of the student to kind of drive through that confusion and get past that point where it's confusing. Because the reality is, once you understand limits, they're pretty easy. But it can be, getting to that point of understanding can be very confusing. Okay, so there's a lot of confusion before you get to that point where it clicks and you're like, oh, now I see what's going on. So, and one of the big things I would say, one of the big things that I see, I haven't taken roll yet, so we'll get to that in a minute. Thanks. A lot of students coming through the educational system have been trained in the K-12 system that a mathematics course is merely about memorizing everything that someone puts in front of you. They put I show you how to do 5 problems on the board, and then you do 40 until you have it memorized how to do the thing. You may not understand what you're doing or why, but you've memorized the process and you can get through it. That's useless. That's pointless. Many of you were lucky enough along the way to not learn math in that way. You had teachers that taught it in a way where you have a much better mathematical foundation, but many of you learned everything in math classes and memorization. We're not supposed to teach that way anymore, and also it's not good for learning. Like learning gets totally left out when you're just memorizing stuff, because if everything is just a memorization of procedures, you'll have forgotten the entire class 3 months after the class ends, right? But if you understand it, then you can carry those ideas forward and use them in the future. So limits is one of those ones where I see people trying to memorize things. It's not going to work. You really have to sort of understand limits from a conceptual standpoint. Now, yeah, a little bit of memorization is fine. You have to understand definitions and remember what the definitions are and understand a procedure. But if you don't have that understanding, that conceptual knowledge behind the thing that you've memorized how to do, it's all pointless, and you're just going to bomb the sections on limits, right? And a lot of this course. So please, especially when we're doing limits, focus on trying to understand. And then if you understand what's going on, then the actual procedures for finding limits are going to make a whole lot more sense to you. Because unfortunately, limits isn't just one thing. Like if we talked to you about factoring, well, factoring's kind of like this. If I say factoring, there's factoring trinomials, factor by grouping. There's difference of squares, difference of cubes, sum of cubes. There's greatest common factor. There's like all these different parts that go into factoring. Limits are the same way. And I would say it's even more confusing, a lot of the language we use with limits. I think that's part of the problem that people have. One, it involves a lot of graphing. So if you struggle with graphs, it's going to be a little bit more challenging for you. But the language is important because the language is confusing to people. I actually think the way that we name some of these things and talk about them it's maybe not the best. Like we could do better, but that's the convention that we use in calculus, and so you kind of have to stick with it. So just kind of beware. If you're finding yourself frustrated in chapter 2, you probably should be. If you're not frustrated at all with anything in chapter 2, then you're probably actually making a lot more mistakes than you think you are. You're probably not really understanding what's going on. Some of these ideas definitely have some subtleties. They're non-intuitive, and they take a little bit of while to sink in and make sense. Okay, so that's where we're going with that. You know when the final exam is, so you know months ahead. No reason not to have that time period blocked off and ready to go. We'll be on campus in a couple of weeks, so make sure you're prepared for that. Try to show up early on day one. I think it's going to be chaos those first couple days back, especially since everyone has to check in and get a wristband. It's going to be nuts. So I would say don't wait till that morning to try to figure out if you're ready to be on campus. Start thinking about it now, right? Upload your vaccine card to the app so you're all ready to go. Because if you have, like, you may be vaccinated, but if you haven't uploaded that card and the school knows about it, you're not getting in the classroom, right? Because we don't have a record that you're vaccinated. Well, I got the shot. Okay, but you didn't upload your vaccine card, so the school doesn't know that. You won't be getting in. So please take care of that stuff. Okay, with that said, let's get back to here. So I have assignments up for sections 2.1, 2.2, and 2.3. I'll get the rest of these up later today. Like I said, that's the top of my to-do list, is getting this other stuff in there. Okay, so chapter 2 is what we're looking at. I think this is a good time to take roll. So let me go through and make sense of this. Let's see. If you are on the YouTube stream only, and you haven't put your name up there yet, please do so I can mark everyone off. Okay, good. Nancy, do you have a last name? Oh, okay, I got you already then. Okay, thanks. Okay, so just to be sure, let's see. People missing that I have marked as missing. Carlos C. Are you? Did we get you there somewhere? Let's see. Carlos C. Tori Franco. Tori F. And I think this person dropped. No. Nadalyn L. Oh, somehow I missed this person. Okay. M. And Stella V. I think that might have dropped as well. Okay. So otherwise I got you. Unless I just called your name, I've got you as here. So that's good. Keep that up. I will say it's really important when we go back to the classroom that you be attending. Keep up that attendance because I've taught this class a ton of times. I'm actually the course coordinator for this class. I've taught it so many times. Students who don't show up don't pass. It's that simple. And it's not because I fail them because they don't show up. It's just because they don't perform in the class. So, make sure that you can show up and that you could be there because we're already kind of crunched on time. We usually have more time in the classroom, but this is a kind of a hybrid. So half the classroom time and then part of it is supposed to be online watching videos. So you've got the videos posted there. The classroom time's really important because there's a lot of information I'm going to be updating you about. Okay, with that said, I think that's all of that stuff. Let's get into the actual mathematics. Okay, so one thing that may be helpful to you is this Desmos site. Don't remember if I've used Desmos yet in this class or not, but it's just Desmos. You just Google Desmos if you've never heard of it before. It's a free graphing utility. In calculus, we are going to be spending a lot of time looking at graphs. We are going to be spending a lot of time going back between the algebra and the graph. Oh, right. And then just to be sure, because I think there's at least one new person in here today. Remember, there's the YouTube stream and the Zoom meeting. So you can be in whichever one you want, but today I'm definitely going to be showing a lot of visuals. So if you haven't already, you may want to hop into the YouTube stream so that you can see what I'm talking about. Because if you're in Zoom only, you're not going to see the graphs and stuff that I'm showing you. And that link is in the top of the Canvas page. So Desmos is a free site. You don't even have to sign up. You can if you want to save your graphs. Like me, I have certain graphs that I use for certain parts of calculus that I've kind of put together, and there's animations and stuff like that. But you don't need to do that for what you're doing. You can just show up, hit this graphing calculator button, and go right in. So you don't need to make an account or anything like that. You just hit graphing calculator. Here it is. So I would definitely recommend you using that because you can graph something relatively easily. You can see what's going on. It's helpful. We obviously won't be able to use this in the classroom because we won't have computers in front of us. But when you're at home working on your homework, like if I was doing homework for a calculus class, I would have Desmos open in a window and then I could graph stuff when I need to. Because like I say, you're going to be going back and forth regularly between the graph and the algebra. The graph and the algebra. Sometimes the algebra is going to help us figure out what to do on a graph. Sometimes what we see on the graph is going to help us figure out what to do on the algebra. So it's not like you can treat them separately. You want to, look at it holistically. You're understanding all the parts and how they fit together. Otherwise, you're really gonna struggle with things. So you come in here and it's pretty easy. You just put an equation in here. How about y equals 2x minus 1? There we go. There's our line. That easily. It puts it in there for us. And with an exponent, you can just use the little caret. So in mathematics programs, shift 6, that little top of an arrow piece is what we call a caret. That's what it's called. That usually gives you an exponent. So if I go back here, I've got an x and I do shift 6. See how it put the thing up in the exponent, and now I can make it a square or whatever exponent it is that I want to put on there. So really simple, easy to use graphing utility, which you're going to want to graph things because this class is like hugely graphing, right? Especially the sections that we're looking at. So I encourage you to use Desmos. Doesn't cost anything. Go in there, make use of it. Okay, let's see. Where is it? I've got the book open somewhere. Here we go. Oh, it's gonna... Man, these online books are always a pain to try to get them. They don't center right when I'm trying to show stuff. Complicated. Okay, let's see. Is that going to do it? Yeah, that should do it. Okay, so we're looking at Chapter 2, Introduction to Limits. So what is a limit? Well, we start doing things in calculus that are more complicated than what you've run across in algebra. Functions start getting weirder, more complicated, and that just goes throughout mathematics. Those of you, if there's anyone, like either you're going to pursue math or you know someone, your brother's a math or sister's a math major or something like that, they're going to take classes that have really, really weird functions in them, things that you can't even graph. They're so weird. And we're kind of going to be doing that. We're going to take a step up now in the kinds of graphs that we analyze. Fundamentally, major parts of calculus are about analyzing graphs and being able to make statements about those graphs. So for instance, we're going to use calculus to find maximums. We're going to use calculus to find minimums. And not just the maximum for the whole graph, but the maximum over a small area. What is the maximum achieved by this graph between x equals 1 and x equals 2? We're going to do things like that. We're going to figure out when are things increasing and decreasing, right? And this is important. If you're making decisions at your job and it turns out that as you produce more units, your profit is actually dropping, well, that might not be a good decision to make, right? You might say, oh, well, why don't we pull back and we'll actually maximize profit? All these kinds of things. We're going to get into high-level analysis of functions so that we can make good business decisions, right? Whether you're deciding how many units to manufacture or how long, like there's examples in the book where we look at an ad campaign. You're spending money on some ad campaign. How do you know when you've spent the right amount of money? How do you know when, at some point, well, for every $1,000 we spend on this ad campaign, we're getting $1,500 in sales? But at some point, once everyone's kind of seen your commercial, starts to kind of not be as effective. So maybe you're spending $1,000 on your ad campaign still, and you're getting $1,010 in revenue. Well, maybe there's some other place you could spend that money that would be a lot more effective. These are the kind of things we want to be able to look at and make statements about. And they're all built from limits, derivatives, integrals. Those are kind of three big topics. And it turns out the two big areas of calculus, the derivative calculus, which we'll get to next time, and the integral calculus, which we'll get to in a few months, the definition for those two objects include the limit. So if you don't understand what a limit is, you're not going to understand the derivative, and you're not going to understand the integral. It's game over. You basically have no understanding of calculus at that point. So everything is built from the limit. And there'll be times when we don't even realize we're dealing with the limit. We'll create these shortcuts where you kind of barely even have to think about the limit. But sometimes we do have to stop and really pay attention to the limit and make sense of it before we can move on. Okay? And sometimes the limit's easy. You're going to do one problem where you look at it and you're like, oh, that's obvious. The answer's 2. And then you do the next problem and you're like, I have no understanding as to what is going on here, right? So again, give yourself a little bit of a break. Realize it's going to take time for you to understand all the different types of problems. But if you keep at it, you get help from me, you get help from the tutoring center, you'll get there. You'll be fine, okay? So what we're fundamentally looking at here, you want to remember this relationship that we see in a graph. So here we have a blue line, right? So if you're on YouTube, you can see what I'm talking about behind me. You can see the visuals. So we have a blue line, which is f of x equals x plus 2. Remember, in calculus, we use function notation very frequently. It's just the notation that's been constructed for calculus relies on function notation. It's a lot more convenient to do it that way. We will have times when we deal with equations, but the default is that you're going to use function notation, and then in a few instances we say, in this case, equations are better, but usually function notation, because you could call this y equals x plus 2, right? But in calculus, we generally use the function notation f of x equals x plus 2 when we're doing that. I think I can make this screen bigger. It's just, let's see. It's hard to get it just right, because, oops, let's just do this one. Let's make it a little bigger. Is that going to look okay if I do that? Just need to move it over a little, maybe. we go. Let me know if the visuals are ever off a little bit or not right, and I can try to make an adjustment. So what do we have here? We have the point 2, the x value of 2, and the y value then would be f of 2. Really important that you're comfortable with function notation in this class, because a lot of times we're gonna use, instead of saying the y value at 2, we're gonna say f of 2. And a lot of people are like, why don't we just say the y? Well, the y is based on the x, and in this case we know exactly what x we're talking about. It's the x of 2 and the y value of 4. So get comfortable with when you see f of 2, you go, oh, that's the y value when x is 2, right? F of 7 is the y value when x is 7, right? So what do we see here in this graph? We see, well, at an x value of 2, you go up and you find the function, and the y value is 4. So f of 2 is equal to 4. Your homework is going to use that a lot. F of 7, f of 3, f of negative 4. And you're going to have to realize, I'm looking for a y value for the given x value. That x value that's in the parentheses, I have to figure out the y value for that particular point, right? So this is just reminding you of that. At an x value of 2, you go up, you find the function, and then the y value, the vertical part, that's your f of 2, that's the y, okay? And, you know, hopefully you remember how to make tables and stuff like that. When we were first doing it in algebra, a lot of times our tables would be like x and y over here, but then eventually we transitioned to where it's x and then g of x for the function g. So this would still just be y values, but it's y values for the corresponding x value, okay? Where's the one I want to go? Here we go. So this is a pretty important understanding. This will help us kind of wade in a little bit to getting an early understanding of what limits are. And remember, there's different versions of limits. We have a bunch of vocabulary. So if you're still a little confused after we meet today, that's okay. This stuff will sink in. Keep with it. So what do we see here? We see a x value of 2 and a y value of 4, just like we saw before. Well, notice what we're saying is, what are all these other lines? Well, as our x values approach 2 from either direction, look what happens. Our y values are approaching 4. You might go, so this is kind of different. Your algebra was always static. It was like a picture, right, where you took a snapshot in time and everything was just one thing. Here's my equation. My x is 2. In calculus, a lot of times you think about things as changing or moving over time. We don't just think about, well, what happens when x is 2? We ask questions like, what happens when x approaches 2? Right? You'll hear that kind of language a lot. And this is what you should be thinking of. Oh, well, there's 2 ways to approach the number 2. I can approach from the larger side, so things that are bigger than 2, like 4, 3, 2.5, 2.1, 2.001, 2.000001. We're getting closer to 2, but from the right side where the numbers are bigger. You can also approach 2 from the left side where numbers are smaller. So think about numbers like 1, 1.5, 1.9, 1.99, 1.9999999, right? We're getting closer and closer to 2, but never actually hitting 2. So as our x's approach 2, what are our y values doing? Well, we have a really well-behaved function in this case, so it's pretty straightforward. As our x values get closer to 2, the corresponding y values are getting closer to 4. Okay? Fundamentally, that's what a limit is. It's not necessarily asking what happens at this point. It's saying what happens as I get close to this point. And we would say, what is the limit as x approaches 2? And you would say, well, the limit of this function here as x approaches 2, that's really asking me what's happening to my y values. As my x's are getting closer to 2, well, my y values are getting closer to 4. So our answer in this case would be 4. Okay, again, this is like a very, very simple version, but that's how you can translate that sentence, right? Because when you look at the actual definition of a limit, it can be overwhelming and confusing. But if you ask yourself, what are the y values doing when the x values are approaching this number? A lot of times that makes sense to students and they go, oh, I'm just looking at where the y values are going. So kind of understand this picture right here, and it's going to help you out, okay? So you can see they're saying, oh, this is the kind of language, or this is how we write it. Oh, and I meant to have that. We'll see if I need that or not, but I was going to prep something. It'll just take me like 10 seconds. But so we just write the limit as lim. So lim, we just say the limit. So whenever you see lim, we say the limit. So you would read this as the limit as x goes to 2. And sometimes you'll hear people say x approaches. So x goes to 2, x approaches 2. Those are both very, very commonly used. So the limit as x goes to 2 of f of x. So then we have to think about, that's the problem we just did. We have to think about it, okay, f of x is my y values. So I want to know, where are my y values going when x goes to 2? Well, we just saw from this picture, the answer is 4, right? So that's why they write the limit as x goes to 2 of f of x equals 4. And obviously that f of x is going to change for every problem, but in this particular case, that's how we write it, okay? Sometimes your limit is going to be the function value itself, like in this case. F of 2 is 4, and the limit as x goes to 2 is also 4. That's because we have what's called continuity. We'll discuss that more in the next section. But like, this is a problem where, you know, you might still be a little confused, but most of you by the end of the day are going to go, that problem's super easy. There's nothing to even think about. It's just right there. But we change the problem slightly, and then everyone gets totally confused. So you want to look out for those little details that are going to pop up. Let's see. Okay, here's our formal definition of the limit. And this is like why I say trying to read this blue-gray box is very different than what we just sort of talked about, which was the intuitive understanding of what the limit is. And you are going to be doing limits from graphs. You're going to look at a graph, and it's going to say, what's the limit of this? And you're going to have to pull it out of there. You're going to be given algebraic functions sometimes, and you're going to have to pull the limit out of that. No graph. You're going to have to look at it and figure out what the limit is algebraically. So you have to be comfortable with both. Can you look at the graph and figure out what it is? Can you look at the algebra and figure out what it is? If so, then you're great. Okay, so we write the limit as x goes to c of f of x equals L. Or sometimes you see this written this way, f of x goes to L as x goes to c. Pretty much we want to use the notation on the left. This is common that you'll see, but it's not really used that much in the book, and it's really not as convenient a notation to use. It just sort of is not quite as clean. So we read this as the limit as x goes to some number c of f of x, those are our y values, equals L, and L has to be a number, right? So they say, if the function value f of x is close to the single real number L, whenever x is close to but not equal to c on either side of c. Now that's weird for people, the but not equal to portion. But not equal to, what that's saying is, like in the previous problem, in this one right here, we don't for our limit, we don't actually care what the function value is at 2. That's not what we're asking, remember? We're asking what happens as x goes to 2, not what happens when x is 2. What happens as x is approaching 2? Okay, so that's what they mean in this definition when they say or not equal to. We don't care about the value at 2. In fact, there might be a hole here. The function might not even be defined at x equals 2. That's not going to change our problem. We don't care if x is defined at 2 or not. We want to know about x around 2 as we approach 2. Okay, so that's what they mean by that part, right? It's a very dense definition. But that's what they mean by the part where they say but not equal to. Okay, yeah.
Could you possibly give us like a real world situation where we would like use a limit?
We will be able to get to that, and you'll see that, but at the moment we can't, because we're just like barely even discussing what a limit is. But you will definitely see those coming up. Basically, we need limits in order to do any of the remaining calculus, to do derivatives or integrals. And then there's going to be lots of examples why you need derivatives and integrals in real life. So yeah, that's a great question that was asked about using these in real life. But you're going to have to wait till we have a better understanding of this stuff, and then we can start to show how to use it. Yeah. But you'll definitely get an answer to that question. So if the function value f of x is close to the single real number L, so in this case, the L, that in the example we did, the L is 4, right? So the y values are close to the single real number 4. So we're not saying they are 4. We're saying they're getting closer and closer and closer to 4. Okay, that's what we want to know about. It's kind of like I forget whose paradox it was. I forget. One of the Greeks was doing work, and they had this idea. I don't think it's Zeno's paradox. I think it's a different one. But this idea that what if I started walking towards the door, and once a second I took a step, and every time I took a step, I halved my distance to the door, right? So that starts off pretty reasonable. I'm 10 feet from the door. A second. Let's start off with maybe a number that's like 8. I start off, I'm 8 feet from the door. 1 second later, I'm 4 feet from the door. A second later, I'm 2 feet from the door. A second later, I'm 1 foot from the door. And then 6 inches, and then 3 inches, and then 1.5 inches. So what's going to happen is you never reach the door, right? Because in any given step, you only half the distance. You cut it in half. So obviously in real life that gets really hard when you start talking about like thousandths of a millimeter. It's pretty hard to have that by taking a step, right? But you can sort of picture you're a beam of light or something going towards the door, and imagine that in each second you just half that distance between you and the door. You're never actually going to reach it. That's kind of what we're doing with limits, which is we don't care about the door itself. We just know we're approaching the door. We're forever getting closer and closer, but we never actually reach the door. Or maybe we don't reach the door. The door is irrelevant in this case, right? But we're forever approaching it. That's the kind of behavior that we want to be able to get our hands on to do higher level calculus. Okay? Here they give you a function notation, right? A piecewise function. I know many people struggled with the function notation. You might want to look over this example. It's kind of a reasonable example to look at. We use absolute values sometimes in some of these problems. But before that, let's see. Before we do that one, let's do this one. Okay. So here we start to see where things get a little bit more complicated. So this graph is the limit of the function is the absolute value of x divided by x. So it's this function right here, absolute value of x over x. So let's look at the graph of that. Okay, so basically you have a line down here at -1, because if you take, say, -5, then you would be taking, the absolute value over x would be -5 over 5. That simplifies to -1. And that's going to happen for any negative x value you put in it. So you get this line at -1. What about up here? Well, if you take the absolute value of x over x, then say you plugged in 1, that's going to be 1 over 1, which is 1. So then you get all these 1 values. But notice what happens in the middle here. I know what happens when I put positive values into this function. I know what happens when I put negative values into this function. But look how we have this weird jump here, right? We're going to talk more about continuity in the next section. But right now, think of continuity loosely as, can you draw it on a piece of paper without lifting your pencil? If you can, then it's continuous. We say it has continuity. If you have to lift your pencil up and put it down somewhere else, then that's probably a jump or a break or some type of discontinuity in your problem. So we have a discontinuity here. Our function jumps from -1 to +1, which is perfectly acceptable. That's totally fine. But then it would make us ask the question like, well, how would the limit be described here? Well, if we talk about this problem right here, I can't have both on screen at the same time. The limit as x goes to 0. So that means we want to know from the left and the right. So as x goes to 0 from the right, well, my y values are 1. Well, as my x goes to 0 from the left side, from the negative side, my y values are -1. Well, then ask the question, what are the y values as our x approaches 0? And if you're looking at this graph, you'd say, well, it depends what side you're approaching from. Are you approaching from the positive side or from the negative side? Right? That right there shows there's a problem. If you have to say it depends what side you're approaching from, then the limit is broken, because we don't have back to our definition, This said there was a single number L that our y values were approaching. We don't have that down here. Some of our y values are approaching 1, and some of our y values are approaching -1. So in this case, there is not one single L value that everything's approaching. So then that's where this comes in. Does not exist, if you can see that. In this case, the limit does not exist. At the limit as x goes to 0 of this function does not exist because our y values are going to they're approaching two different values. So we can't kind of make that work. Now, what if I said the limit as x goes to 1 of this function? That does exist. That would just be 1 because the y values are all approaching 1. What about the limit as x goes to 2 of this function? That would be 1 as well because our y values are all approaching 1. In fact, they are 1. They're approaching it. So what you're going to find is the limit is based on a point. So you might have a function where like here, the limit at 0 does not exist, but the limit at 2 does, right? So the limit is based on the point you're asking about, not the function altogether. Okay. Let's see, where are we? Okay, which brings us to one-sided limits. Okay, great. Here we go. Get it right like there. Okay. So one-sided limits. So this is a little different. It's almost the same notation, but see how we have the limit as x goes to c and then a little minus right here floating above the c of f of x? That tells us we're concerned about the one-sided limit from the negative direction. So we're approaching this from the left, from the negative side of things. We're coming in and approaching that way. Down here we have the limit as x goes to c, and then there's a little plus. That means we're approaching from the positive side. We're coming from above the number and coming in that direction. So when we just say the limit is understood to be a two-sided limit. You have to be worried about coming in from both directions, and they have to be going to the same place. The problem we just had, that wasn't the case. One was going to 1, one was going to -1. They don't meet up. Okay. Here with the one-sided limits, we're only concerned about one side at a time. Okay, so if we go back to that picture we were looking at, the one-sided limits do exist in this problem. So if I wanted to look at the limit of this function, if we wrote the limit as x goes to 0 and then a little plus next to it, that means that we're concerned about this one right here as x goes to 0 from the positive side. Well, what happens to my y values as x approaches 0 from the positive side? Well, the y values are all 1. So in that case, the one-sided limit from the positive side would be 1. Okay, and the same with the negative side. We'd say, okay, what if I had the limit as x goes to 0 but a little negative sign there? So it's the one-sided limit from the negative side. Well, then all my y values are -1. Okay, well then the one-sided limit in that case would be -1. So the two-sided limit doesn't exist because the two values don't agree, but the one-sided limits on their own do exist. Okay. Feel free to ask questions if anybody has any along the way. Okay, and then so then they just hear on the existence of a limit. For a limit, whenever we just use the word limit, it's understood we're talking about a two-sided limit. If you're talking about a one-sided limit, you have to be specific. This is, and you'll sometimes hear people say from above or below. Above means from the positive side, below means from the negative side. So if you just hear someone say limit, understand that's two-sided limit. If they say the one-sided limit from the positive side or the one-sided limit from below, then we are specifying the one-sided limit. So for a two-sided limit to exist, the limit from the left and the limit from the right must both exist and be equal. So sometimes people get confused and they're like, oh, well, both of my one-sided limits don't exist, so they're equal to each other. No, in mathematics, if one thing doesn't exist, that's not equal to another thing not existing. There's nothing there. If it doesn't exist, how can it be equal to something, right? So they must exist, in other words, a number, and be equal. So in the problem that we just looked at, the one-sided limit on one side was -1. The one-sided limit on the other side was +1. Well, both of those one-sided limits existed, but they're not equal to each other. One's -1, one's +1. Therefore, we could conclude that the two-sided limit, what we just called the limit, does not exist. Okay, I know I'm piling a bunch of stuff here. We got limits, one-sided limits, two-sided limits, limits from one side, limits from the other side. It's a lot to keep track of, I know. But that example we looked at, the two one-sided limits exist, but they don't agree. Therefore, the limit does not exist. And then they just have like a mathy version using like calculus notation of saying the same thing. This says the limit as x goes to c of f of x is equal to L if and only if the one-sided limits are equal to each other. That's really all that means. Okay, so let's see. I don't want to show that one. So here's an example right here of a graph where if we look at this graph and we're talking about the values as x approaches 1, well, if you look at 1, what do you notice? The function isn't even defined at x equals 1. There's like a hole poked in it right there, right? That's what that open circle means, is like a hole's poked right there. But we can still ask the question about x is approaching 1. So as x approaches 1 from above, from the positive side, it looks like our y values are they're getting closer and closer to 3. So that would mean that would be this middle one right here, the limit as x goes to 1 plus. So the limit as our x's approach from the right, our y values up here are getting closer to 3. Well, the same thing on the other side. If we approach from the left, as x goes to 1, right here, our x's are getting closer on the number line to 1. Our y values are getting closer to 3. So we'd say the limit is 3. In this case, both of the one-sided limits exist, and they agree. We got 3 for both of them. That means the two-sided limit exists, and it is also equal to 3. Even though the function value itself doesn't even exist at 1, the limits at 1 do exist in this case. The two-sided limit and the two one-sided limits both exist. So that's helpful, right? So the question was asked a few minutes ago, like, well, when would I ever use this? And trust me, all of calculus is built on limits. But here's kind of the first case. What if you have a function that you're trying to study, and you want to know the behavior at a certain x value, but your function's not defined at that x value? Well, with the tools of algebra, you'd be out of luck. You'd go, I don't know, the function's not defined at the place you're asking me about. What do you want me to do? Calculus says we can still gain information. Even though your function is not defined at a certain value, we can still gain information about what the function is doing around that point. Okay, that's hugely powerful, right? Hugely helpful. Here is another example. So let's say that we have this function and we want to know about the limits as x goes to 2. Okay, well, if I approach x going to 2, let's go from below, so I'll just keep the same order. As x goes to 2 from below, look at our y values. It looks like they're coming down and approaching 2. So the limit as x goes to 2 from below of f of x would equal 2, because that's where our y values are going. They're approaching 2. But look how we have this discontinuity. We have this jump right here. Well, on this side, if my x's are approaching 2, my y values are up here. They're actually getting closer to 5. So that one-sided limit is 5. So one of my one-sided limits is 2. The other one is 5. Well, those don't match up. Those don't equal each other. So the two-sided limit does not exist. But in this case, look, the function value does exist, but we don't really care. Remember, in the limit, we don't really care if the function is defined or not at the point that we're wondering about. And at first that kind of seems like that's weird that we don't care, but it's actually really powerful. It means if we have a function with an undefined point, that's not going to stop us from doing calculus on that point. Okay? Right, like I say, feel free to ask questions if you need along the way. Okay, then there's this whole big thing of properties of limits, which are helpful. But the truth is, most of the time when you're doing this, you're going to have homework assignments that ask you to break down these particular problems. But most of these are going to become so second nature to you that you don't even think about them. You just automatically use them. So this says a few things. What if we have the limit as x goes to c of k, it equals k for any constant. So what you want to do is not just read these, because most people when they read these, they're going to go, I don't know, it looks like we discovered some alien language. That stuff is crazy. I don't know what any of that means. Try to make sense of it. So for instance, the limit as x goes to c of k, where k is a constant. So what would that look like? So let's jump over to Desmos. Well, they're talking about like a situation where y equals, say, 3, right? That's a constant function. Y equals 3. Just like you can have your bank account, if you don't have any withdrawals or deposits, your bank account could have a constant, could be $1,000. You have $1,000 in the bank. You're not adding money. You're not taking money away. The graph of it would just be a constant function, 1,000 all the way across, right? So this is a constant function. Well, at any given point, if I want to know about the limit, what would the limit be? Well, let's take it. What happens at 6? Well, as my x values go to 6, what are my y values? 3. What about at -2? As x values go to -2, what are my y values? 3. There's just 3 everywhere for a constant function. Therefore, the limit at any given point on this function, the limit will be 3. Right? So that's really all this means. So sometimes I know what it's like. You read something out of the book and it just seems so confusing. But like when you actually work it out and look at it in a graph, you're like, oh, this number 1's like, first of all, it's not that confusing, but also it doesn't really seem that important. The limit as x goes to c of a constant is just that constant. Yeah, that makes sense because that's what all the y values are, right? What about this one? The limit as x goes to c of x equals c? Wait, that's confusing again. Nope, all that's saying is that if you have the function y equals x, then think about it 2. As your x values are approaching 2, what are your y values doing? They're approaching 2. What about at 4? Our y values are approaching 4. So you can guess. What happens at x around x equals 100? The y values are approaching 100. That's all that's saying, right? So nothing too fancy. This is really convenient for algebra. It means we can break up our limits with respect to addition and subtraction. That is super convenient, right? There are certain areas of mathematics where we can separate things with a plus, and there are certain areas of mathematics where we cannot. Square roots is one. In algebra, people do this all the time. You have the square root of 5 plus 9, and people try to break it up into the square root of 5 plus the square root of 9. Can't do it. Doesn't work. You can't break up square roots with respect to plus or minus. The great news is we can with respect to limits. So why would you do this? Well, what if your f of x plus g of x was really complicated and you were getting confused? You could break it down into 2 smaller problems and figure out the limit of each one of those functions separately and then just add your 2 values together. That's all that's saying, right? And so why would you do this? Well, you might have a function where the first term involves an exponential, so you're going to have one set of rules for exponentials. And then maybe your second term has a logarithm, and we're going to have a second set of rules for logarithms. And then maybe your third term is a polynomial term, and your fourth term is a rational expression, right? So I'm just kind of piling on, making it ridiculously complicated. But we have 4 terms, all of which are going to have to be calculated in a very different way. Well, then it makes sense. Why don't I just break it into 4 different sub-problems, and I'll just tackle one at a time? That's what this allows us to do. So very helpful. Okay. This says if we want to multiply our limit, like multiplying the function by a constant is the same as just multiplying the limit by a constant. We can break things up with respect to multiplication, and then you get a couple down here about we can take the limit of the top over the limit of the bottom, and you can move things around. But we'll sort of come back to those as we start using them. You'll have homework problems that use them. So you can see, like here, you have homework problems like this where they say, find the limit as x goes to 3 of x squared minus 4x. Well, using those properties above, they say, well, then I can break that down into the limit as x goes to 3 of x squared minus the limit as x goes to 3 of 4x. See how we've broken it down into 2 smaller limits now? You go, okay. Well, now I've got the limit of x squared, according to those rules up there. I can break that down into the limit of x times the limit of x minus 4 times the limit of x. So this is using that one rule about bringing the constant out front of the limit, number 5. That's what gets used right here. And this one is using the product limit, which is number 6 right here. So they're just progressively throwing more tools at this until it simplifies down to the point where we can just calculate it. Because remember, this one is number 2. That was our rule number 2 we just looked at. The limit is x as x goes to 3. Well, that should be 3. And then here we have minus the limit as x goes to 3 of 4. And then you just simplify everything. So those of you who have been exposed to calculus before, at some point in the class, we start learning some shortcuts for some things, but you also have to know how to do things the proper way, which is the long way. So that question usually comes up in a calculus class where someone's maybe taken calculus in high school, but didn't maybe get the grade they wanted or something, and they're like, well, can I just use the shortcuts? No, you have to be able to do both, right? Mathematics is not just memorizing a bunch of shortcuts. It's about understanding the material. So, and then you need to understand where those shortcuts come from. Why do they exist the way that they do? But we'll be getting into that more throughout the chapter. Okay, let me find my place. Oh, here we go. Limits of polynomial and rational functions. This is convenient. I know many of you hated polynomials and rational functions in pre-calculus or college algebra, whichever one you took. In calculus, you love polynomials. It's one of the simplest functions that you can do calculus on is the polynomial. It's really well behaved, and many functions are going to be much more complicated to deal with. So number 1 says the limit as x goes to c of f of x equals f of c for any polynomial function. So what's going on there? Well, let's remember back. Any polynomial is continuous, right? We kind of looked at a couple problems where there were weird breaks or holes poked in the problem or something like that. Polynomials don't have that. They're defined everywhere and they're continuous. And what you're going to learn in the second section of this chapter is that continuous functions behave really nicely from a calculus perspective. So since polynomials are always continuous, that means they're going to be easier to deal with. So if you want to find the limit at a certain point of a polynomial, all you have to do is plug that point into the polynomial. That's really nice. That's an easy calculation. That you're basically doing back in algebra where we used to say evaluate, and you would just say, they would say evaluate this function when x is 3, and then you would change all the x's to 3's, and then you'd simplify. That's what you're going to do. Right? So this number 1 might seem, a little weird if you're still getting used to the notation. Hugely powerful because it's going to allow you to find the limit very, very quickly. You just plug the value in there. So for an example, the limit as x goes to 2 of x cubed minus 5x minus 1, all you have to do is plug 2 in there. And that's what they're doing right here. They take the polynomial and they plug 2 in for x, and you get negative 3. That's about as easy as you could hope for, right? That's pretty straightforward. Okay, what about for rational functions? So the limit as x goes to c of your rational function is equal to r of c for r, any rational function with a non-zero denominator at x equals c. So remember with rational functions, so that would be things like, let's say x squared minus 1. Oops. Squared minus 1 over x squared minus 5, something like that. So a rational expression, you get these weird kind of different shapes. So notice that for most of this graph, it's continuous. It's only really discontinuous where it has an asymptote, right? In fact, if we clean this up, I can graph them. So 4. So that's going to happen what? At x equals 2 and x equals negative 2. At x equals 2 and negative 2, that's the only places where we get a discontinuity. The rest of these, you can draw them without lifting your pencil off the paper, right? So that means they're continuous in these areas. The only place this function is not continuous is at x equals 2, because we have this jump discontinuity, and at x equals negative 2, because we have another jump discontinuity. So the good news is, as long as the place you're trying to find the limit isn't 2 or negative 2, then your function is continuous, and we can use the same procedure you did for polynomials, right? Don't try it at 2 or negative 2, because then you're going to get 0 in the denominator, and you're not going to know what to do with it. But if you use it correctly, It's simple too. Just make sure you're not doing it at a discontinuity, and this rational function is easy to figure out. So see what they do here? The limit as x goes to 4 of 2x over 3x plus 1. And what are they doing? They're just plugging in 4 for x, and they get 8/13. Again, that's a pretty easy calculation to go through and do. Okay? Yeah, okay. So those are convenient. Those will really help with things. Yeah, more you've got your piecewise function, but it's more just the same stuff. Oh, right. Let's talk about this function. So let's do this one. To have this in the right spot, I basically, my window is split onto 2 different screens. So that's why I keep getting a little disoriented. I have to keep looking back at the different screens here. Okay, let's make this x squared minus 4 over x minus 2. So this is a rational expression. And when I get them both on here so you can kind of see the thing. X squared minus 4 over x minus 2. And you go, that looks like a line. Isn't that just a straight line? You're telling me it's a rational expression, but I'm used to rational expressions having asymptotes and undefined points and, you know, they're kind of weird, creative looking. That just looks like a line to me. Technically, it's not a line, and it might look like it because if I also graph the line y equals x plus 2, you go, what are you talking about? Those are the same line. Look, they're right on top of each other. How are you telling me that first thing is not a line? Technically, it's not a line. The graphing utilities don't do a good job of graphing these, but for the second graph, I can plug in any x value I want, and I'm going to get back a y value, right? Just pick any number you can think of. You can plug it in there for x, and you add 2 to it, and you get your y value. Can you plug in any number you want to the top one? Try plugging in 2. You get 0 in the denominator, and everything screws up. So, well, then why am I not seeing that when I look at the graph? Well, technically, we have, let's see if I can make this look okay. Usually I can't, but let's see if I can do this. So we've got, let's see, equals, I don't even know what to make it equal to, 1 or something. Let's make this, it's going to be what? X minus 2 over y minus 4. And then let's make that way, way smaller. So it's like 0.1, 0.01. Oh, that's too small. Okay. So it really should kind of look like this, where it, like, imagine the purple line was not in there. You know how we have the empty circle to indicate there's a hole right there? We kind of just looked at that in the book. Technically, that's what this should have, is a little hole right there, right? A little hole poked in it. So it doesn't exist at the point x equals 2. Every other place it acts just like the line y equals x plus 2, except the red one has a hole poked in it right there. Okay, so we can still figure out the limit at x equals 2, but there's no function value at x equals 2. So you're going to see a couple problems like that. So how do you figure that out? Well, you recognize that if you factor that top, in fact, they probably do it here in the book, don't they? Let's see. Yeah. So what you do is you take, if you want to know the limit as x goes to 2 of x squared minus 4 over x minus 2, what you do is you simplify this thing. You factor the top, you do your canceling, and then you end up with, oh, the limit as x goes to 2 of x plus 2 equals 4. And you go, but wait a minute, I thought the function wasn't defined at x equals 2. But remember, in the limit, we don't care if it's defined at 2 or not. We're talking about the behavior near x equals 2. So what this means is, for this function right here, as our x values approach 2, our y values are approaching 4. We don't care if the point 24 exists or not. We're not even concerned about it. Like, you tell me, oh, no, there's a point there, 24. I don't care. We're doing a limit. It doesn't matter if it exists or not, right? So, so just be aware of problems like that pop up. those are pretty straightforward. Okay, indeterminate form is a thing that's going to pop up throughout the semester. We'll return to it later. So you just kind of want to know what it is. So if the limit is x goes to c of f of x equals 0, and the limit is x goes to c of g of x equals 0. So we have two different functions now. We have a function f, and we have a function g, and both of them are approaching 0 for the same x value. Then this limit is said to be indeterminate. And specifically, it has 0 over 0 indeterminate form. We will return to that later in the semester with a thing called L'Hopital's rule, which is a ridiculously easy way to calculate some really hard to calculate limits. If you have two functions, f and g, and you make a quotient out of them, if the limit as x goes to c of the denominator function goes to 0, then the limit itself will not exist, because you get really weird behavior if the y values so you want to remember this frequently throughout this course. You want to be able to walk through this. We kind of talk about this in like pre-algebra, but sometimes people forget, or sometimes people are so panicked about fractions they're afraid to think about fractions, but you want to understand them. If you have a fraction, little numerator, big denominator. What does that mean for your fraction? Is that going to be a big number or small number? Big denominator means small fraction. Okay. Big numerator means big fraction. You know, relative. When you're comparing the numerator and denominator, if your denominator is much larger, your whole fraction is going to be small. If your numerator is much bigger, your whole fraction is going to be big. So in this case, what happens is if your denominator is approaching 0, that makes the whole fraction blow up, right? Like you think about like 1 over 1, 1 over 0.1, 1 over 0.01, 1 over 0.0001, 1 over 0.000001. Each of those terms is blowing up, right? So if your denominator is shrinking to 0, your function can do really weird stuff. So you just kind of want to understand that can happen. And always think back to this. Again, don't memorize things. Think back to this fraction and go, okay, this problem I'm working on has a big fraction with a small, like the fraction's blowing up, but the numerator's shrinking down. Oh, that means that this whole thing's going to 0, right? Just think about it in terms of those fractions. And I would highly encourage you to open the ebook like I'm doing when you do the homework, because you're probably going to want to look at different examples while you're doing this. Okay, limits of difference quotients. So now we're starting to combine things that are complicated, right? Limits, you're probably already sort of, we barely even talked about limits, but you're kind of wrapping your brain around limits and going, that's a little confusing. Now we take some of people's least favorite thing from pre-calculus, which is the difference quotient, and we're taking the limit of a difference quotient. And it may seem like, are you just trying to torture us? You're just taking like the worst combination of things and putting them together? Why would you even do that? Well, it turns out the limit of the difference quotient is the definition of the derivative, which is it's one major branch, like 1/2 of calculus is derivative calculus. So it turns out the limit of the difference quotient is a hugely, hugely important idea that you will be practicing. So they're just trying to slip them in now so that you get used to the algebra, because honestly, people struggle with the algebra in that section. So they're just getting you used to it. But we will technically define the derivative as the limit of the difference quotient in section 2.4. I think it's in 2.4 where we talk about that, if I remember correctly. So you can just follow along with the example that they have here. Basically, you're just substituting stuff in there. And that's our chapter 2. So let's see. Or section 2.1, I should say. Okay, so with chapter 2, then, we get into what are called infinite limits. Now, this gets confusing because infinite limits play by a different set of rules than limits that we just talked about. So even if you watched limits and you're like, yeah, that was not bad, I totally get it. Infinite limits is like related, but kind of a different ball game. And then to add to the confusion, and I wish we had a different naming convention, because I literally like have discussions with students and I can see how confused they're getting, but unfortunately it's what we call them. We have infinite limits, and then we have limits at infinity. And unfortunately, those are not the same thing. So you have to be careful to realize, when am I talking about an infinite limit and when am I talking about a limit at infinity? They're very different ideas, even though the wording is almost identical. So, and then I'm gonna confuse it even more with the way we discuss these things. So I'm kind of gonna read here a little bit. I'm not gonna read the whole thing, but I want to make sure you kind of, follow along with how this is being presented, and probably want to read this page a little bit when you get home because it's confusing, right? So I'm going to explain it, but when you're doing the homework, read it and go, okay, I think I'm starting to understand what he's talking about. So let's say we take the graph of f of x 1 over x minus 1, f of x equals 1 over x minus 1. And if we look at the limit as x goes to 1 from above of 1 over x minus 1, let's take a look at that. So let's go. So we can see what they're talking about. Y equals 1 over x minus 1. And we can see it's undefined at x equals 1, so we can kind of call out that vertical asymptote right there. So, okay, so that's what we're talking about. So we have 1 over x minus 1. The limit as x goes to 1 from above of 1 over x minus 1 Oh, right. Okay. I was thinking of a different problem. So what happens here as we approach 1 with our x values, so we're starting here on the right and we're approaching 1, what's happening to our y values? Well, in the problems we were doing earlier, usually the y values were approaching like a certain value. But look here, they're just getting bigger and bigger. And the closer I get to 1, the bigger and bigger my y values are going to be. They're just exploding without bound, right? If we got close enough, our y value would be 10,000. If we got close enough again, our y value would be 100,000, and then a million, a billion, a trillion. The closer we get to 1, that value is just shooting up. Well, remember our limit says you're approaching a specific number. Well, in this case, we're not approaching a specific number. We say approaching infinity. And infinity is a weird thing. The more math you take, you just keep revisiting infinity, and it gets weirder and weirder. All the way into grad school, you start seeing really bizarre stuff with 0. But it starts getting weird in calculus. So as our x values are approaching 1, these y values are shooting up and approaching infinity. So that's what they're saying here. The limit does not exist. This one-sided limit does not exist because for the limit to exist, it has to approach a specific number. So there does not exist a real number L that the values of f of x approach as x approaches 1 from the right. Instead, as x approaches 1 from the right, the values of f of x become larger and larger without bound. And we say it goes to infinity. Let me move this over. So it's kind of weird. We would write it this way. F of x, the limit, sorry, I'm looking at the wrong one. The limit as x goes to 1 from the right of 1 over x minus 1 is equal to infinity because that's where the values are going. You want to think in this case of infinity as a verb. It's not a noun. You don't reach a point on the number line where you're like, okay, everybody, there's a final stop. We're at infinity. Everyone get off the train. We're here. You don't ever reach infinity. It's like a verb. You're going to infinity, okay? But this is weird because technically the limit does not exist. So it's weird that we're giving an answer for something that doesn't exist, right? Like that definitely confuses some people because they want to write like does not exist. You're right, it does not exist, but we're describing the way in which it does not exist. Because if you look, well, on one side, our values are shooting up towards infinity, but look on this other side over here, the values are shooting down towards negative infinity. So both of the one-sided limits do not exist, but we want to describe the manner in which they don't exist. This one's going to infinity. This one's going to negative infinity. So that's why you see those kinds of answers. It's more specific than saying it does not exist. We are telling you the behavior and the fact that it does not exist. But that's weird for a lot of people that like, wait a minute, the answer doesn't exist, but you want me to give an answer anyways? Yes. The answer is yes. Okay. So this is what we call infinite limits. That is, the limit is either infinity or negative infinity. That's infinite limits. Okay, and you can kind of see what's going on. This is like from our problem. We take numbers that are closer and closer to 1, and look what's happening. Our values are just blowing up bigger and bigger. All right. Okay. Let's see. Where do I move? Just like that. Okay. So infinite limits and vertical asymptotes. The vertical line x equals a is a vertical asymptote for the graph of y equals f of x if f of x goes to infinity, if it goes to negative infinity, as x comes in from the left or right. So basically what we were just looking at, you know what a vertical asymptote is. You just got, you learned that in algebra and pre-calc and all that kind of stuff. Locating vertical asymptotes of rational functions, because that's usually where you're going to see vertical asymptotes, is in your rational functions. So basically, if you take your rational function and you simplify it, if f of x equals n of x over d of x, so they're using n for numerator and d for denominator. In this book, they usually name functions a thing that makes you remember what it is. So n is the numerator of your rational function, and d is the denominator of the rational function. If d of c is equal to 0 and n of c is not equal to 0, then the line x equals c is a vertical asymptote of the graph. In other words, it's the way you used to find them in pre-calc. What would you do? Your vertical asymptotes were where your denominator was equal to 0. Remember, you'd be asked the question, where is this rational function defined? And you'd find all the places the denominator was 0 and say it's not defined here. And then 99% of the time, those ended up being a vertical asymptote. Well, that also means that your one-sided limits at those vertical asymptotes is either going to be infinity or negative infinity. Okay. So like here, if we have this function right here, what would we do to figure out where this thing's undefined? We'd take x squared minus 1 and set it equal to 0 and get 1 and negative 1. That's where our vertical asymptotes exist from pre-calc. Well, what we're saying in calculus is you're also going to get infinite one-sided limits at those vertical asymptotes. Okay, so you're relying really heavily on the algebra from pre-calc in order to now do what is actually the calculus step here is like pretty easy. You're just labeling something that you figured out algebraically. So the way you found those undefined points in algebra, that's like 90% of the work for the problem. Once you find those, you just name them and go, oh yeah, now we know how to figure out the limits at these points, right? Because see, you can see x squared minus 1. Remember, those are going to be undefined at negative 1 and positive 1. So you can make a table and you can see, oh yeah, this one's shooting down to negative infinity. And this one's shooting up to positive infinity. Okay, so you get that kind of behavior in those places. Let's see, locating vertical asymptotes. Yeah, we got that. So there's numerous examples, but it's the same thing again and again. And they kind of, if you're having trouble, they can help you figure out, when do I say a limit does not exist, and when do I put infinity or negative infinity in there? Basically, for the one-sided limits, if it's infinity or negative infinity, you're going to put those values in there. When you use the two-sided limit, remember the two one-sided limits have to agree. So if both of your one-sided limits say infinity, then we would just say infinity. But we know in our hearts, like, oh, that's actually, the limit doesn't exist, but the values are shooting to infinity, right? It's kind of a subtle point that I know doesn't make sense at first, but okay, now we have this other part that people confuse. What we just did was infinite limits. Now we're doing limits at infinity, which, sounds confusing. The good news is, like 90% of what to do here from pre-calc. You don't know what it is that you're supposed to do, but what I'm saying is you already learned like 90% of what we need to do limits at infinity. It's basically end behavior. So I know people got annoyed with that. People don't always love limits at or end behavior when we're doing it in pre-calc, but if you can calculate that end behavior, you've got it. That's basically what we're doing here. So now notice the wording is a little bit different. This says the limit as x goes to infinity. Oh, now the infinity's down here. So what does that mean? Well, that means you're on the x-axis and you're just moving to the right forever, going to infinity. Or you're on the x-axis and you're moving to the left, going to negative infinity on the x-axis. So you're either just shooting to the left forever or you're shooting to the right forever. In the case that we have infinity, then we're moving to the right because positive infinity is to the right. So we're really saying, what do the y values do in the end behavior? As when we're way down the line for this function, what are the y values doing? And this is what you can get a horizontal asymptote. But I referred to this last time, and I said there was a little box in your homework that we're going to refer back to later. Oh, I thought we were about to get to it. Is it? Maybe I'm thinking of it being later in the book. Where is it? Should be this section. Did we move it? Here it is. So this is the calculus version of that gray page that I don't remember if it was on like page 58 or somewhere around in there, but it was talking about end behavior. If you read it and you understand the calculus notation, this is literally the same box, except it's now in the language of calculus instead of the language of pre-calculus, right? Now we have limits in here. Instead of talking about end behavior, we talk about the limit at infinity, okay? So what are we looking at? The limits of rational functions at infinity and horizontal asymptotes of rational functions. So like if you have a polynomial, then each end either goes up to infinity or negative infinity, and they can go different ways. But when you look at one end at a time, it's either going to infinity or going to negative infinity. That's for a polynomial. For lines, unless it's a horizontal line, or not counting horizontal and vertical lines, if they have a normal slope to them, then one end's going to infinity, one end's going to negative infinity as far as end behavior. The place where it gets interesting is with rational functions, and we can get horizontal asymptotes. So say we have, this is just how we write things in calculus version. So this is some rational function. Notice that all the coefficients in the numerator are a with a subscript on it. That's just the coefficients, and they're matching it up with the exponent or the variable to an exponent. So a sub m x to the m, that's just the first term in your polynomial in the numerator. And then we just decrease the index by 1 each time. So this was different when we dealt with quadratics in algebra. I'm going to go a couple minutes over, but there's some pretty important stuff I want to point out here. When we were doing algebra, we'd have like ax squared plus bx plus c. So each coefficient got its own letter. Well, in calculus, you sometimes deal with really big polynomials, and it's annoying to just use all these different letters because then you get confused like, wait, is this letter from my first function or my second one? If we all call them a's, then we know, oh, that's part of the numerator function, and all my b's are part of the denominator function. So it's really about organization, right? But what we want to know is, what are the limits as x goes to infinity or x goes to negative infinity for a rational function? Well, the good news is it's just the end behavior, but it's in the language of calculus. So remember I was talking about like the relative sizes of your numerators and denominators and what that does to your fraction. Well, think about it this way. If your denominator is bigger, if it's growing at a faster rate than your numerator, that's shrinking your whole function down. So if the degree of your denominator is bigger than the degree of your numerator, then this is case 1, then your limits at infinity will be 0 because that blowing up denominator shrinks the whole fraction down and it approaches 0. Okay? That's the same, like I'm going over, so I don't want to take too much time. But if you go back to like page 58 or whatever, you're going to see the same description, but it's in terms of end behavior. But it's just exactly this right here. If m is equal to n, that means the degree of your numerator and denominator are the same size. That means the numerator and denominator are getting bigger at the same rate. So what it's going to be is just the ratio of the coefficients in front. Okay. So it would be a to the m over b to the n. That's what they're saying the limit is right here. All right. That's kind of like, so let me show you an example. Let's do this. If I've got, let's move this over so you can see the function too. Let's say we've got x squared over x cubed minus 1. So here's a function I just made up. This was case 1 where the denominator is bigger degree than the numerator. And look what's happening to our function. It has a horizontal asymptote at y equals 0. It's because the denominator is growing faster than the numerator and shrinking the whole fraction down to 0. So right around like in our normal area, you're getting, you're getting some interesting behavior, but eventually that blowing up of the denominator smashes the whole function down towards 0. So this is case 1. We're seeing case 1 being used right here. Okay, the one we just talked about, what if we made, let's just make it simple, x squared. Okay, so here's another function. I've now changed the degrees. The degree of the numerator is equal to the degree of the denominator. So then we take the ratio of the coefficients. 1 over 1 is 1. And sure enough, look at our end behavior. These are approaching y equals 1. So in this case, you would say that the limit as x goes to infinity is 1. Okay, because that's where we're leveling off. And then if the degree of your numerator is bigger, then these things just shoot up towards infinity. You might recognize, if you had a teacher who went over it, these are what we call a slant or oblique asymptote. In calculus, we don't usually care that they're oblique asymptote. We just say, well, this one's going to infinity, this one's going to negative infinity, and we go from there. Let's see. Let me double check there's not anything else super important that I want to point out. Yep, that was what I wanted to get through. Good. So I took a couple extra minutes, but you need to spend some time with section 1.1 or 2.1 and 2.2. If you try to wait and do this stuff at the last minute, you're gonna regret it, because it takes a little bit of time to make sense of this. You're invited to come to office hours and ask me questions. The tutor center is going to be great with this stuff. The people in the tutor center know all about limits, and almost all of them have taken calculus, and most of them have taken the engineering calculus, so they're pretty solid with limits and derivatives and stuff. So those are both good places to get help. And then make sure you understand these, because again, both the definition of the derivative and the definition of the integral involve a limit. So if you don't understand limits, the derivative is just going to be a bunch of you're going to memorize a bunch of stuff and probably use it incorrectly, because you won't actually understand what's going on. Okay? So work on that. Next time we will pick up, I'll talk for a couple minutes about continuity, but that doesn't require too much of a conversation. And then we're going to get into the derivative, which is a pretty big deal, right? I'm kind of telling you it's half of calculus is derivative calculus. So it's a big, important branch of calculus that we're going to introduce. And the derivative is going to open up a massive number of tools for us to use to analyze functions and make use of things that are important to us to figure out, okay? So start working on the new homework assignments. I will basically right now start putting up the other ones for the rest of the chapter. So you'll have those. So you've got a couple weeks to do all of the homeworks for the chapter, but really don't wait, because even 2 weeks, you're going to be busy doing them. Even if you do it daily, it's going to keep you pretty busy. So don't procrastinate on those homework assignments. Okay. So thanks, everybody. As always, I will stick around in Zoom. So if anybody wants to ask me questions, come talk to me in Zoom, and I'll help you out with whatever it is you want to talk about. We'll talk about it. Otherwise, I will see you later. Okay, thanks, everybody.